So my name is HUNG Shih Wei. I'm now a research associate in material science and engineering, and also the CHESS Center. So now I'm working with Professor Chen Furong. So it's my pleasure to share our recent research progress of our center. So in the beginning, I would like to introduce our center. So CHESS means time resolved operation corrected environmental, and TEM means transmission electron microscope. So the mission of our center is to provide a user platform using a high time space resolution TEM to solve the advanced scientific problem in different environments. Also, another mission is to develop the electron optics related technique. So in our center, there are 4 teams. One is source material in situ imaging, and theory and TEM imaging analysis, magnetic, orbital, and dynamic imaging, and electron optics design and review manufacture. So I'm taking care of a theory of TEM imaging analysis. So today my content is more related to this topic. So Richard Feynman in 1959, in his famous talk, "There is plenty of room at the bottom," he said, "It would be very easy to make an analysis of any complicated chemical substance. All one would have to do would to look at it and see where the atoms are." So he stressed the importance of the electron microscope. So here shows the evolution of spatial resolutions. So the red line means the optical microscope. So the limitation is around 0.5 micrometer. And the green line is the electron microscope. The limitation is around 1.7 angstrom. With the operation correlator, we can push the limiter to sub-angstrom. So here is one example of one of our members took. So here we can see the every atom in the image, and from the diffraction pattern, we can also determine the structure. Also, we can determine each elements. So currently, our electron microscope technique has met the Feynman's expectation. But there are still some bottlenecks of current microscope. One is radiation damage. Here, the example is about the dose rate dependence of hydrogen bubble generated in situ photocatalyst. So we put the TiO2 nanoparticle into water, and because of the photocatalyst, the hydrogen bubble will generate. And in this experiment, they find the bubble will generate quicker, faster if we using higher electron dose rate. So this result means when we observe the physics in TEM, we also included not only the photocatalyst, but also the radiolysis. So it means the electron radiation will change the physics of observing systems. And next is a lack of temporal resolution. So if we use a poor temporal resolution, we can only observe the equivalent states. So here I use the anti-simulation of a single layer graphene to illustrate. So here is the time resolution is about 1 nanosecond. We can see the graphene layer is very flat. But if we increase the time resolution to 100 times, then you can see, so you can see the vibration of a graphene. You can see the wave-like vibration of graphene. So it means with average in a long time, the fluctuation will be smoothed out. So currently, the temporal resolution of TEM is around second to milliseconds. So comparing with the spatial resolution, the temporal resolution is still poor. And another bottleneck is a lack of 3D information. So here is the photo image adapted from the TEM textbook. So it shows when we see this photo, we think it's funny because we will not think it is a two-handed rhino because we have already know the 3D nature of rhinos. But in TEM, usually we don't know the 3D structure of materials. So when we see in TEM, because it's a 2D projection, so we need to be aware of this, or we probably will give a wrong interpretation. So in our center, actually in Microscope Society, we aim to solve these problems. So here in our center, we also try to solve these problems. So in our latest installed TEM, we have a bin chapter in the bin source part. So use the bin chapter, then we can generate pulse electron beams. So using the pulse electron beam, we can reduce the electron dose rate. Also, we can also reduce the radiation damage. And we also have an ultra-fast camera. And in cooperate with the electrostatic sovereignty system. So the temporal resolution can reach 20 microseconds for one-shot images. Also, we have faster focal series recording systems. So we can take a series of through focus images. And using the algorithm developed by Professor Chen, we can retrieve the 3D information of the material. And here we'll introduce the method. So conventionally, we try to look at the clear image. So to see clear images, we need to use a high dose. Yeah. So usually here is a number of like STEM TEM, scanning TEM, HRTMs. But for the beam sensitive materials, if we give too much electrons, we cannot see it. Actually, we cannot see it with this electron beam because the material will be damaged. So here we propose, Professor Chen proposed another method called low dose electron hologram. So here we are not looking at a single image. We are interested in the exit wave. So for TEM images, we view electron as a wave. So exit wave is a wave at the exit plane of the sample. So this wave included 3D information of atoms of samples. So we will disperse the total dose into focal series images. So for each image, the dose is lower compared with this one. And also, then we use some mathematic algorithm. We can recover the edge wave from these focal series images. So, and if we obtain the edge wave using different period, we can also obtain the dynamics. So the structural change with the time. So here is one example published by Professor Chen last year. Here is MOS2 nanoparticle. So because we use this method, we can reduce the dose rate to like 25 electron per angstrom square per second. So because the dose rate is very low, we cannot see the material for every single images. But after we apply the method, then we can reconstruct the edge wave, and then from the face of edge wave, we can clearly see the nanoparticle. So here, from the edge wave, then we can first we need to determine the position of each atomic columns. Like here, we can determine the position of each atomic column, and then we will propagate the wave at different defocus. So the maximum of intensity of propagation wave means the position of the exit plane. So according to this, use this criteria, we can determine the 3D of each atomic column. And then because we use a different period to reconstruct the exit wave, so then here we can obtain the dynamic of the narrow particle. But for this method, there's one problem. We need to obtain the resolved atomic column. Like, we need to see each atomic column. But for some material, we cannot see clearly the atomic column. So here is an example. So twist bilayer graphene now draw a lot of attention because we can change the electric property by change the structure, like the twist angle, strength, and the interplanar distance. And for twist bilayer graphene, actually we cannot see the atoms. So here is an example. This is a Tokyo model. I rotate the top layer like 90 degrees, and then here you can see the fringe. We call it a Mori fringe. So actually, we see in this image, it's not the position of atoms, it's interference of electron. So, and the Mori pattern formed due to the periodicity arising from the superposition of similar layers. So for this material, we cannot use the above method to reconstruct the atomic structure. So here we develop another method. We call it simulated annealing and energy minimized method. So here is a demonstration. Here we have the initial model is a disordered structure like this, and we want to recover it to FCC structure. So simulated annealing is optimum algorithms. So using this one, we will change the position of each atom. So then we can calculate the image of this model. Then we will compare this image, calculated image, and the experimental image. So it will go down. So it means the difference between two images. So this will going down. Then it means our structure will approach to the experimental images. But because this our simulation image is not sensitive in along the direction of electron beam directions, like here shows. So from the top view, the face is very good. It's close to the experimental ones. If you look at from the side view, it's not good. So here we also apply a method called energy minimization. So we will give a potential function to describe the interaction between each atoms. And then we will also move the atoms so the overall potential will reach the minimum. So after apply energy minimization, then we can recover this disordered structure to the FCC structure. And so here is our result from the experiments. So this is a focal series image taken from our new latest installed TMs. So this series picture is taken by our member, Dr. Li Xiaoshui. And the sample is prepared by our collaborator, Professor Lu Yang's group. So here we took a focal series from minus 67.5 to 67.5 angstrom. The explosion time is 0.2 seconds, and we took total 200 images. So as we showed before, you cannot see anything in one single image. But after we reconstruct the wave, then you can clearly see the more pattern of bilayer graphene. And after we obtain this reconstruct wave, then we will use we will refine the structure. So the initial structure I created is from the pristine graphenes, and the twist angle is determined by the diffraction patterns. So here's a movie. So we will do the SA and the EM interactively. So after around 20 iterations, we can obtain identical results. So here is after the optimized results. Here's the experimental results. So then so by this process, we can also obtain the atomic models. Yeah. So I also using 25 image to reconstruct the wave, as wave. So here we can obtain the time resolution. So for this case, the time resolution is about 5 seconds. And here is the similarity between the simulated and the experimental wave. So I use this cross correlation function to indicate the similarity. So I think for our current results, the similarity is very good. So after we obtain the dynamics, then we can create. Here is a movie of these bilayer graphenes. So since we know the structure of each atoms, so now we can calculate some structural properties. So here, first we calculate the displacement map and the strength. So the green is a pristine graphene, and the red is the one we construct from the experimental. So by comparing these two structures, then we can obtain the displacement in x direction and the displacement map in y direction. And we can use the simple equation, this displacement map. And then we use the relations, then we can get the strain x and the strain y and shear strength. Here is a summary of the stress and the shear stress at different times. And next, because we're also interested in the interplanar distance. So since we know the z direction of each plane, so we can calculate the interplanar distance. So I also plot the interplanar distance distribution at different times. So from the result, it shows maybe the distance change with time is not large. We can the distance change slightly in the time we observe. And next is the twist angle distribution. So usually we use the diffraction pattern to determine the twist between two planes. But the diffraction pattern is average properties. So from the diffraction pattern we know the averaging twist angles, but we cannot know the twist angle locally. And since we obtain the position of each atom, so we can calculate the orientation of each hexagon. Then we can, using these orientations, then we can determine the twist angle distribution. So we can know the twist angle locally. So maybe this one will help for the next step, since we know the locally twist angle distribution. And that's all of my analysis. So here is the latest conclusions. So to study the 3D dynamics of soft materials, the pulse, low dose inline electron holograph is very important. So like we will not damage our materials. And we can also obtain atomic scale dynamics. And here we also develop the simulated annealing energy minimization method to accurately retrieve the 3D structures, marine material. So besides to the bilayer graphene, we are also working on like carbon nanotube and other biomaterials. So that's all my presentation. And I would like to thank the support of our team. And thank you for the attention.